what we have to do today. So I'm sure you are now used to how to do the standard forms and then how to do the decimal places. So let's do two more questions and then I can move to what I want to do today. Okay. So let's pick a question in a fractional form and solve and see whether we can have the results. So I'm doing question number 44. Simplify 3 over 14 minus 2 over 5 plus 2 over 35. Let's see whether we can do it and have our answer. So we have 3 on 14 minus 2 on 5 plus 2 on 35. So LCM, something common to all of them, is what we need. So if you look at 14, if you look at 5, if you look at 35, you ask yourself what number can be common to them. There's no number coming into mind immediately. So I did tell you in class that when you can't find any number or you don't seem to find any number that is common to all of them, what you do is that you multiply all the numbers at the denominator. So we multiply 14 by 5 by 35, and then we record it here. That is what you can do when you are not finding a common LCM to them. You multiply 14 by 5, you multiply that by 35. So before that as well, you try and find out a number that you think can go into 14 easily. And that same number can also go into 35 easily. Because you know 5 can go into 35, but 5 cannot break 14 down. So the another way to is to try multiplying 14 by 35 to see what you will get. If what you have, you feel 5 can break down, then you can use that one as well. So the other thing is also by multiplying 14 like this. So you ask yourself, can 35 break down 70? Can 5 move into 70? Can 14 move into 70? Yes. So then you settle on a lower figure. So if we use 70, it means 14 will come into 70 5 times because we just multiply 14 by 5 to get the 70. You multiply the 5 by 3, and then you have 15 minus 5 comes into 5 goes into 70 14 times. So when you multiply the 14 by 2, you have 28 plus 35 goes into 70 2 times. 2 times 2, you have 4. So you have 15 minus 28 plus 4. 15 plus 4 will give you 19. So then we do 19 minus 28. 19 minus 28, we have negative 9 divided by 70. We can't have any number to cancel this 9 and then this 70. So we have negative 9 over 70. But if you look at the results we have here, we have 17 over 30, 17 over 210, 1 over 30, 1 over 210. Our answer is not in. Then you think of board mass. The board mass we did. BODMAS. So let's try and arrange it in a board mass way and see. Over 14 plus 2 over 35 minus 2 over 5. So we have our LCM again. You could either multiply all of them or you can multiply 2 of them and check whether the other can cancel it. So the same thing, I'm using 14 by 5, which is 70. 14 will move into 75 times. 5 times 3, you have 15, plus 35 moves into 72. 2 multiplied by 2 is 4, minus 5 goes into 70, 14. 14 times 2, 28. So you see that you still come and get the same 19 minus 28, which will still give you negative 9 over 70. So now that you are sure that if you use board mass and go by the order, and then you just arrange them the way it is, and you check your answers here, and you cannot find your answer. If you are working this as an objective and you don't find your answers here, what I expect you to write is that you write E on your paper, E, and then you write your answer, negative 9 over 70, because your answer cannot be found in these objectives. And probably the answers sometimes are typed wrongly. So once you are sure of the method you have used and you are not finding your answer, you write your answer like I did. So you can look at it in both ways. I told you that in board mass, whenever you have minus and plus, you can do the two at the same time. And then if you also want to follow the board mass, 35 first before the minus, you see that both ways you get the same results. And once you get the same results and your answer is not here, you write your answer. So this is one of the things I wanted to show you today. In order for you not to make your mind that sometimes when you are sure of what you have done, because you are not finding your answers in the objectives, you leave your answer and you try and go and shade any of them because you are thinking your answer is wrong. All right, so let's look at one more example and then I can move to another thing today. So I'll pick another simplification question number 70. So let's work this one and see whether we can find our answers within the options we have here. So you have 1/3. Then you change all mixed fractions into improper fractions. So 6 multiplied by 2, that is 12 plus 1, 13. So you have 13/6 plus 6, 5, 30 plus 1, 31 on 6. Last week, I told you that this divide here, if you see several divides, you have to change this one. I'm seeing divided by 3 here, divided by 6, divided by 6, before this big divide, and then come to divided by 12. The division sign are clear, so I'm seeing 1, 2, 3. So we need to convert this middle one to the traditional one we know. So instead of this long divide, we bring divided by this way, and then we can change this one. 12 times 1, 12, plus 7, you have 19. So that's 19/12. Then you have a straight line equation like this, right? Brackets first. So let's work what is within the brackets. We find our LCM. LCM is 6. 6 here, 1 times 13, you have 13 plus 6 here, 1 times 31, you have 31. So when you wrap up the top, you have 13 plus 31, and that's going to give you 44 divided by 6. Into bracket 44 divided by 6. Then you have this divided by 19/12. So we proceed. We multiply 1 by 44, and then we have 44. We multiply 3 by 6, and we have 18 divided by 19/12. Then we use the law of reciprocity to break this one down again. So we have 44 divided by 18, and then we change the division to multiplication. And then the 12 comes up, and then the 19 comes down. So then we start our cancellation. So we say 3 goes here, 4, 3 goes here, 6. 4 and 2, even numbers. 2 goes here, 2, 2 cancel 6 or so, 3. At this point, 3 cannot cancel 44, 2 cannot cancel 19. So it means we need to multiply the top and then the down. And this is what we do. 44 multiplied by 2, you will have 88 divided by 19 by 3, you have 57. So we have 88/57. And then we go check our answers. Checking our answers, all our answers are in mixed fractions. So it means we need to do something about our 88 divided by 57. So then we do the long division you were doing some time ago when you were kids. 57 divided by 88. So 57 will go into 88, 1. And then you take off the 57 from the 88. When you do that, you'll be left with 31. And because 57 is bigger than 31, you can't continue. So it means that your final answer now 57. And that is E. The answer is E. So this is the two more examples I wanted to add before we start our new topic
Hello,
today.
sir.
Yes.
Yeah, please, it's like the final answer you got during the long division method was 57 over 31.
Which side? This one.
Yeah, the down.
Yes, so this is the answer we had. We had one whole number. The remainder was 31.
Okay,
So 31 divided by 57.
okay,
Yes, so that is how it is written. You
okay,
always bring the remainder on top
okay,
and then you divide it by this one.
okay. Thank you.
Okay, sir.
Right.
Sir, please, I have a question.
Hello?
Yes, sir. I have a question, sir.
Yes, go ahead.
Yes, sir. So on the long division that we did, the normal long division that when the divisor is bigger than the number, the 57 is the divisor bigger
Mhm.
than the 31. So I was thinking we add 0 to the 31 so that we continue, or that's how it's supposed to be.
Yes, yes. You can do that, but you see that when you do that, you are going to get a decimal. But all the answers are in fractions. Are you
Okay,
getting it?
okay, yes, sir.
All the answers are in fractions. So if you put a point like this, like you're saying, and then I add a zero and I continue, I can't even find the answer here because all the answers are in fractions. They are not in decimals. Assuming they were in decimals, then we'll have to put a point, add zero, and continue.
Okay,
You try and look
okay,
at the answers that has been arranged. All
okay,
right.
okay, sir. Okay.
Okay, so yes, that is good. Another time we can look at more exercises, but we want to start our new topic today, our unit 2, which I have titled as Algebra with Mathematical Operations. All the things we have done right from the time we started these classes, I can see that we were seeing numbers. There were no alphabets. It's numbers, everything numbers. So we were dealing with the number systems, which we called it as arithmetic. So arithmetic mainly deals with numbers. Now we want to move from the number system and want to deal with alphanumeric. This is arithmetic is only numeric, but we want to move and deal with alphanumeric. And alphanumeric is a combination. I think most of you are old enough to understand the difference. Alphanumeric is a combination of alphabets and numbers. So alphanumeric, combination of alphabets and numbers. And when you have such situations, we call it algebra. Algebra. So today we will encounter algebraic expressions. Algebraic expressions. It means that expressions that you have numbers and alphabets. Okay. And we want to just refresh our minds quickly on certain things you've come across in your mathematical life before, finding the volume of an item, finding the area of a land, finding the perimeter, of an area using formulas to get results, writing expressions in the form of algebra, factorizing them, expanding them, simplifying them. So everything is algebra, algebra, algebra. And one more time, algebra is a combination of alphabets and numbers. Alphabets and numbers. So let's start from the simplistic way. Now, if I write an expression like this, 12 plus b, 12 plus b, okay. Now, the b you are seeing here is called a variable. B can be small. It is unknown. But what I know is that as for 12, I know 12. So 12 is known. When somebody mentions 12, you know how 12s look like. Example, if I say I have 12 cities, you understand me. If I say I am 12 years, you understand me. Okay. But when I say I am B years, you won't understand me. Or I have B cities, you won't understand me. Why? Because B is an unknown value, which may change or may not change. As for 12, 12 will never change. 12 is 12. So that is known. But the one that you don't know is what we call the variable. And what you don't know. When you put such expressions together, we call them algebraic expression. Algebraic expression. Putting together quantities that you know and then quantities that you do not know. So you could see expressions like this: a plus 2. I have an unknown and a known. So this is an algebraic expression. I have a times b, unknown. I have 3m plus 6n minus 6. I know 3. I don't know the value of m. I know 6. I don't know the value of n. I understand 6. So we are going to simply look at algebraic expressions and the various properties that can put them together. Now, what we do in maths is that we use what we know to find what we do not know. So you use what you know. Now, the technical terms that are used in algebraic expressions, we want to start looking at them. When you hear the word coefficient or coefficients, coefficient is like a support. What we don't know. Okay. So let's look at example. When you see me write an algebraic expression like this, combination of alphabets and numbers, 6m plus 5. If I ask you to find me the coefficient, I just want the number that comes before the alphabet. So this 6 is the coefficient of this expression. Any number that supports the alphabet is called the coefficient. So I have 8R plus 7M plus 4. In this case, I have two coefficients. 8 is a coefficient to R, and then 7 is a coefficient to M. So my coefficients are 2, 8 and 7. The third expression, I have 14B minus 8. 14B minus 8. So the 14 is the support for the unknown B. And so 14 becomes my coefficient. Now, the other technical word we want to learn today of an algebraic expression is the word term. The word term. Term is the name given to either a number or a variable or a combination of a number and a variable. So three things. A term refers to one, only a number standing alone can form a term, or a variable, which are the alphabets. It can also represent a term, or a combination of a number and a variable. That's the third scenario. That can also represent a term. Let's demonstrate that. If you take the same expression and I ask you, how many terms are you seeing in the various expressions? Okay, if I pick the first one, by definition here, a number can be called a term, a variable can be called a term. A is a term, 2 is a term, and then together I have 2 terms in this expression. The second example, I go back to the definition. A term can be a number standing alone, a variable standing alone, or a combination of a number and a variable. So I have one here, a combination of a number and a variable. And a variable. This is going to be my second term. A number standing alone. This is going to be my third term. So it means I have 1, 2, 3 terms in this expression. And so these are 3 terms as shown. 3m, 6n, negative 6 terms. So that is the second technical word we want to learn today, in addition to the coefficient. Now, we want to now look at some simplifications in algebra. We want to look at some simplifications in algebra. Sometimes you can be given a multi-dimensional lines of algebra. So what I mean by that is they will give you various combinations. For instance, I'm seeing 3t here. I'm seeing 7t here. Secondly, I'm seeing 5w squared here. I'm seeing 4w squared here. And then thirdly, I'm seeing 9v here. I'm seeing 8v here. Once they are combinations of numbers and alphabets, all of them are forming a term. So these are terms. But is there a way to simplify them? Yes. Sometimes it is good to put the terms together. So I can add 9v to 8v. Why? Because they have the same structure. So 9 vein and 8 vein, I can put them together as 9 vein plus 8 vein, and then I'll have a total of 17 vein. So instead of writing the two of them, I'll use 17 vein to represent the two of them. And then after that, I'll pick 3T and 7T and put them together. So I have 3T plus 7T, and the two will give me 10T. So 10T can also represent 3T and 7T. And then finally, I pick 5W squared plus 4W squared and put them together. So I'll have 5W squared plus 4W squared. And this gives me 9W squared. That can also represent 5W squared and expression has been reduced to 10T like this plus 9W squared plus 17V. So we have used algebraic simplification. We have used algebraic simplification to simplify a 6-term line to a 3-term line. And that is the first property we want to discuss, that anytime you have a lot of algebraic expressions, is there a way to put them together to form a different shape? Yes, that is possible. Now, there are other things also that we can work out from algebraic expression. The other property is that all the combinations you see, anytime you see a constant is a number. It's not an alphabet. Anytime you see a constant, the sign, the operational sign, whether it is positive or negative or division or multiplication, the sign follows the constant. I can't leave the negative sign in front of the 2. The negative sign will have to move with the 2. So when I want to cut this term off, I'm going to cut it this way, and then the constant will be -2. It is not 2. If you write it this way, it is wrong. The sign will have to follow it as you move it out, because the constant never changes. It never changes. It's the same wherever you move it. So anytime you see constants in algebraic expressions, carry the sign in front of it with a constant. Don't leave the sign behind. Now, putting all together, if I ask you a simple question, the coefficients and the constants of the following algebraic expressions. So this is a short quiz. Identify terms, coefficients, and constants. So this is what I can do I'll just draw my table this way from this end to that end. I will then label the first column or block as terms. I'll label the second column. I'll label the third column as constants. These are the three demands from the question. So I'll take them one after the other. This is the first question. This is the second. This is the third. And then we have the final, which is the fourth. So let's get to action. How many terms do we have here? We said a term, by the definition of a term, we said a term can be either a number or a combination of the two, numbers and variables. So let's check. This is a combination of number and variable. So this is our first term, number and variable, second term, number alone, third term. So our terms are 12a, comma, 6b, comma, and then 4. These are our terms. And then the coefficients by definition are the numbers that are supporting the variables. So let's see the numbers that are supporting. So I see 12a. So 12 is a support. 12 is a coefficient. I see negative 6b. So negative 6 is a coefficient. As for 4, we cannot pick it because it is not a combination of alphabets and numbers, so it's not giving support to anything. And then we come to the constants. Constants, by definition, are only numbers. They are only numbers and not alphabets. So when we look at this, the constant is also supposed to be picked with its sign. So this constant is positive 4. And if it's positive 4, we normally don't bring the positive, so we write it as 4. So this is our first line answer. Our terms are 12a, 6b, and then 4. And then we come to the second one. The second, our terms are 4x. It's a term by definition. And then 2y is also a term. And then we look at the coefficient. The coefficient, the first coefficient is 4. The second coefficient is negative 2. What about constant? Let's check whether there is a constant. So when you check this one, there is no number standing alone. So that means that there is no constant. We put our dash there. We don't have a constant for the second expression. And then we move to the third expression. We have an and then we have 32, a number also standing alone. 32 is also a 10. And then let's look at the coefficients. So let's see the support. What is supporting C? Normally there is 1 here. We don't normally write the 1, but there's 1. There's 1 before any letter. So it means that the coefficient of C is 1. And then we go to constant. So here, constant, it should be a number in isolation. So when we isolate this number, we have the constant to be negative 32. So you record your negative 32. And then we come to the final one. The final one, we have 3x plus 2. 3x plus 2. So let's check our terms. 3x is a term. So we write our 3x. And then 2 is also a term. We write 2. What about by 3? So 3 is a coefficient. Apart from that, we don't have any variable here. So 2 cannot be a coefficient. And then we move this number. We have positive 2. When it's positive, we don't normally write the positive, except it is negative. The moment it's negative, we write it. But when it's positive, we hide the positive sign and write this one as 2. So if you ask me that, now record the total number of terms, coefficients, and constants. This is what you do. The total number of terms for all the 4 expressions, we count them as 1, 2, 3, 4, 5, 6, 7, 8, 9. So the total number of terms for the 4 questions are 9. What about total number of coefficients? You have 1, 2, 3, 4, 5, 6. So we have 6 coefficients in total. And then we look at the constants. The constants, we have 1, 2, 3. And we have a total of 3 constants for all the 4 questions we have looked at. Any question about these 3 technical terms, coefficients, and constants in algebraic expressions? Any question before I move on to the next thing I want to do? Yes, Abraham.
Yes, sir. Please, I didn't get the last part where the 9, 6, and the 3. How did we get it?
Yes, so we are counting every column, we are counting the total number of things we have recorded.
Okay.
So this is 1, 2, 3,
Okay.
4,
Okay.
5, 6, 7, 8, 9.
Okay.
So we're just counting them.
So
Any other question?
I think
Yeah.
the previous page, when you add the numbers, you separated the numbers from the alphabet. So let's say not here. So we have that you wrote this part. So when it comes to this side, I was thinking maybe like let's say 3t and then the 7t. Then we have 3t plus 7t equal to 10t. So nothing happens to the t.
Exactly. Before you go on with your question, this is how they look like. I want you to understand. So don't lose your thoughts. I will let you continue with the question, but the what you said, the statement you said, I want to enhance it. You said 3t plus 7t is equal to 10t. So your question is nothing happens to the t, isn't it?
Yes, please.
It's very good. Nothing happens to the t because now t can represent something like sugar.
Okay.
It's so actually the variables are representing in real life, they are representing items.
Okay.
They are representing items. So 3T plus 7T is like me telling you I have 3 grams of sugar
Okay.
and I'm adding it to 7 grams of sugar.
Okay. Okay.
Uh, so at the end of the day, I'll get 10 grams of
Okay.
sugar.
Okay.
So
Okay.
nothing happens to the sugar.
Okay. Okay. Okay.
And that is how it works.
Okay. Okay.
In the same way, the W square is also representing another item.
Okay.
And then the V is also representing another item. So you can continue
Okay.
with your question.
Yes. So that's all. Please.
Yes. So to the whole class, with the question Abraham has asked, it is very, very important because if you don't see the alphanumerics as representing items, you will see it as abstract mass, and then
Uh-huh.
you will not appreciate it because when you see it like this, plus 3t squared plus 4w4 plus 3k cube plus 7t squared plus w4. Now, this is a clumsy structure. So those who don't like math is because of this. This is the reason why a lot of people see math as abstract because they can't figure out this thing in their mind. That what is this? What is this? But these are alphanumerics or algebraic expressions that are telling you that there are some items that are changing. And those items that are changing are being represented by an alphabet. So I see K, I see T, I see W. So all you do in alphanumerics is that, is there any way we can put some of them together? So if I see 5K cubed and I see 3K cubed, I can see their variables are the same, K cubed, K cubed. So it means that this K cubed is actually representing a certain first item. It is not abstract, it is just a representation. Then after that, I see another one. I see t squared. I see another t squared. So it means that because they are all t squared, I can put them together. So that t squared I'm seeing is also representing a second item. And then finally, I see w to the power 4. I see w to the power 4. It means I can put the two together, which means that this W4 is also representing a third item. Is what item is this representing? What item is this representing? What item is this representing? That is why we call them unknown. We need to find out. But the numbers in front, as for 5, you know the meaning of 5. You know the meaning of 3. You know the meaning of 4. You know the meaning of 3. You know the meaning of 7. You know the meaning of 1. So the moment we discover that the first item, which is KQ, is representing, let's say, a line, and then the T squared is also representing probably lemon, and then the W4 is also representing maybe orange. Then after finding that this is the meaning of our expression, it means that this long expression you are seeing, we have a combination of a lime plus lemon plus orange. So these are the items: lime plus lemon plus orange. But in what proportions or quantities are they? That is where we put the numbers together. If I pick the K cube, which is representing the lime, so I have 5 limes plus 3. So in all together, I have a total of 8 limes. And then when I pick T squared, once I know that T squared is also representing lemon, I look at the quantities. I have 3 here, I have 7 here. So I have a total of 10 lemons. And then if W4 is also representing orange, when I put them together, I have 4 oranges here, I have 1 here. When I put it together, I have 5 oranges. So now the story is complete, that you have 8 pieces of lime in addition to 10 pieces of lemons and then 5 oranges. So these are representations that we do. So don't get confused at all when you see this combination. Some are squared, some are not squared. Don't get confused at all. They are all representation in algebraic expressions. I hope it is clearer now.
Yes, please.
All right. Any other question? All right. So if there's no question left, now we want to come to real life. We want to apply. We want to apply all the algebraic expressions we have learned this morning. We just want to see how we can apply this in real life. In real life, there are a lot of stories. And sometimes the stories we see with algebraic expressions. So this is actually a language, another way of speaking to your audience. We want to represent stories and real life situations with algebraic expressions. So let's start gradually. Let's start with the fundamentals. So I'll use a word phrase and then we'll change the word phrases into algebraic expressions. These are the simple ones. Three more than a number. 3 more than a number. Which number? I don't know the number. So I'll represent the number by X. Then I check 3 more, not 3 less, 3 more. So in maths, when you see more, you represent it with the addition sign. So if you say 3 more, it means plus 3. So then the final representation will be that 3 more than a number will be X plus 3. This is how we can use just this one letter and then one number to represent this sentence we have constructed here. If you count this sentence in words, we have 1. So this is a representation of 3 more than a number. We don't know the number, so we use X to represent. And this is where the alphanumerics comes in. We have an alphabet which is representing what we don't know. And then we also have 3 that is representing what we know. So a combination of what we don't know and what we know is the statement we have made here. Now, second phrase, the quotient of a number and a 8. The quotient of a number and a 8. The quotient of a number and a 8. So the quotient, we don't know the quotient, but they have given us a number. So normally when you are doing a long division, you will see that there is a number you divide, like the way we were doing this morning, dividing 57 by 88, like this. Okay. So when you see quotient, it means long division is coming in. The quotient divided by 8. And we use this one to represent the statement. The quotient in long division, when you are dividing a number and another number, the number you are dividing, which goes inside like the 88, comes first, and then the number, which is the divisor, comes below the sign. So this one, if you remember, originally it was 88 divided by 57. Okay, so that is the second statement. Now the third statement, I can say 6 times a number. 6 times a number. So 6 times is the same as 6 multiplied by a number. So we know 6, we don't know the number, so we represent by a variable. And then 6 times, this is the multiplication sign. So it means that 6 times n, and then you have 6n as your result. So this 6n is representing 1, 2, 3, 4 words in terms of the word phrasing. Then we have 15 less than a number. 15 less than a number. We did 3 more than a number as our first statement. 3 more than a number. This time we have 15 less than a number. So we don't know the number. We represent the number by any alphabet, so Z. 15 less is not the same as 15 more. 15 more would have been positive, plus. But 15 less, so you have negative. 15 less, it means you have a negative. So that is why you are having Z minus in alphabets and numbers. But this time, we are translating word phrases into algebraic expressions. Now, sometimes you can have compound or complex ones like number 5. So if you look at the fifth one, it's longer than all the rest. It says the quotient of 30 and a number plus 10. Look at the words. Quotient, number, plus. Okay, So the moment you see quotient, let the long division concept come into your mind. Okay, the quotient of 30 and a number. So 30 and a number, x, plus 10. Then you add your plus 10. And this is representing this long sentence you are seeing here. So there are story problems in which we'll be coming across word phrases where we need to change the word phrases to algebraic expressions. And I'm sure as we proceed till we close today, we may come across some of them.
Hello.
Now, as for, yes, is there a question?
Yes, the previous page, sir.
Yes.
Yes, go ahead.
Can you go to the previous page there?
Pardon me.
And can you go to the previous page? The previous page.
I should go to the previous page. I don't know who is.
Yeah.
Yes.
Okay. The first example, 3 more than a number. Then the representation is x plus 3. So, sir, in that scenario, 3 more than a number, can we change the position and the 3 can
Exactly so.
what the variable?
Exactly so. Exactly so. Yes, 3 more than a number is the same as 3 plus x. You can change the position.
Same applies to number 4 as well.
Number 4, you can also change the position. So that one you need to be careful. 15 less, 15 less means that the negative sign will have to follow 15. So in that case, you write it like this. Are you here? Yes.
Yeah. So number 2, the quotients of a number and 8.
Yes.
Then when you look at 5, it says the quotient of 30 and a number.
Yes.
So this one, you will see that the alphabet, the number that we are not given is divided by 8. But when it comes to 5, the number you are given divided by the number you are not given.
Yes. So you just watch the order. The
Yes.
quotient of a number.
Yes.
So the number comes first.
Yeah.
And a 8.
Yeah.
And this one, the quotient of 30, not a number.
Yes.
The quotient of 30. So the 30 comes first before the number you don't know comes. I think your line is not too clear.
It's okay now, please.
Right. Okay. Thank you for the question. So this is what is good Abraham was asking the question he asked because I was bringing you to this page to show you the various terminologies that you may come across in which you need to be grounded, else you write the expressions in a wrong way. So let's look at words that can be used to describe addition in algebraic expressions. And then we look at words that can be used to describe subtractions in algebraic expressions. So the first word for addition is that you can see the word add, or the question will say plus, or sum, or total, or increased by, or more than. These are all words that are representing the addition sign. And then what about the subtraction? The subtraction, you have minus, you have difference, you have subtract, you have less than, you have decrease by, and then you have less. And this morning we have seen two of them already. In the example we did, we saw more than in the question whereby they said 3 more than. And then we've also seen less than. The last question we saw as 15 less than. So it's not, these are not the only words that you should expect. All these other words can be used to represent either the positive or the negative conditions. And then, as you know, we have 4 basic operations: the positive, the negative, the multiplication, and the division. So now you know the words for addition. So for words that are used to describe multiplication, there are not too many. We have 3 of them. So or multiply. And then when it comes to division, you may see only these 2 words: quotient and divide. Or times in one of the examples, and then we saw quotient in the other example. So it means that we'll be using them constantly to solve a lot of the algebraic problems. And I'm sure you will not forget these keywords for addition, for subtraction, for multiplication, and for division. So these are the basic algebraic operations. Symbolically, as you know already, the positive connecting two algebraic expressions, the negative sign connecting two algebraic expressions, the multiplication also connecting two algebraic expressions, and then the division sign also connecting two algebraic expressions. Let's then look at more examples. Once you have understood the phrases, let's look at a few more examples. So the first example is 4 more than S, the letter S. 4 more than the letter S. Just as I was explaining to Abraham, you can write this one in 2 ways. You can write it as S plus 4 or 4 plus S. 4 more than. So there's supposed to be a positive sign. This more than a signal is giving us a signal that the positive sign will have to show up somewhere. So when it comes to positivity, the variable and the number can interchange positions. Any of them can come first, the other will come last. Then second word phrase, the product of 7 and C. The product of 7 and C. As for this one, you can't write it in two ways. You can only write it in one way, because in algebraic expressions, you always write the number first before you bring the variable. So the product of 7 and C. So we have 7, product means multiplication, C. And this will give us 7C. You cannot write this one as C times 7, which is equal to C7. No, this is wrong. This is not how to write algebraic expressions. In algebraic expressions, always the number or the support, the coefficient, will have to come first. Third example, 9 less than x. So the less than is also connoting something we learned today. Less than means there's a negative somewhere. 9 less than x. This also, you cannot write it in two ways. 9 less than, the less than is affecting the 9. So you have x minus 9. X minus 9. When you write it this way, minus 9 plus x. You have introduced two operations. Meanwhile, the question is only one operation, less than. So you shouldn't write it this way. It should rather be the first way. 9 less than x means subtract 9 from x. So that is the third one. Now let's look at the fourth one. The fourth one says that a number divided by the sum of 4 and 7. So now I'm seeing a lot of operations here. A number divided. So this is division. A number divided by the sum of 4 and 7. So sum is what? Plus. Okay, so we have two operations here. Now let's wrap it up. A number, we don't know the number. So let's represent the number by x. It says divided. A number divided by the sum of 4 and 7. So a number divided by the sum of 4 and 7 means 4 plus 7. So this becomes the expression. A number divided by the sum of 4 and 7. So we have represented the fourth one. Now let's look at the fifth. It says twice the sum of a number plus 4. Twice the sum of a number plus 4. So twice the sum plus of a number plus 4 plus So first of all, plus 4, x plus 4, x plus 4. It says twice. Twice means 2 times. That's what twice means. Twice means 2 times. So twice the sum of a number plus 4. So this is how it will look like. Twice, the 2 is representing the twice. Twice the sum of a number plus 4, right? Then we have the sum of 3/4 of a number and 7. The sum of 3/4 of a number and 7. So we don't know the number. The number is x. But they say we should find 3/4 of the number. So 3/4 of the number is 3/4. Let me use another letter to represent the number. So let's use y like this. So yes.
Number 5. So twice the sum of a number plus 4. Why don't we maintain the x alone in the bracket and the 4 will be outside? Or because if both the x plus the 4 they are inside the bracket, is the 2 outside the bracket not affecting the 4 also?
Oh, you are right. You are right. You are right. Twice the sum of a number plus 4. You see,
yeah.
I even wrote the plus here. I've left the last plus. That's good observation. You are right. So twice the sum. So it is this 2 times x plus 4. You are right. You are right.
Thank you.
You are right. Yes. Thank you for that observation. Twice the sum. So I even wrote plus here. Good. Let's look at the sixth one. The sum of 3/4 of a number and 7. So the sum, it means plus will show somewhere. The sum of 3/4 of, the of is normally multiplication. So times 3/4 times y plus 7. This is how it's going to be. So finally you have 3/4 y plus 7. 3/4 y plus 7. Because of your intervention, Abraham, I want to be sure if the class is following. So please, if you have a question, ask before I do the last one. If you have also observed anything in our writing, you can ask a question and then I can continue, because I want to make sure you fully understand this, and then we can use it to solve a lot of problems that we are required to do. So if you have a question, please ask. If you have any intervention too, you can bring our attention to it, because we are learning together. So if you've observed anything, let's go back and look at it. Else we can continue with what we are doing. We'll be writing the answers. Okay. Once I'm not seeing any hand up, I think I can continue.
I think.
Yes. Is there a hand up?
Yeah. Can you go over the other one? The sum of 3/4.
Okay. Okay, so let's go back to the sum of 3/4. I think this place is too untidy. Let me clean this side so I can move up. And then we can write them. So we are going to have two terms for that question. It says the sum of 3/4 of a number and seven. So let's look at it. So this is what I did. Sum means plus. Now 3/4 of a number. So it means that the sum, this one plus, is here. It means that find 3/4 of a number and then add it to 7, which is standing. And I was saying that 3/4 confuse my multiplication. So I used the letter Y that is the same as 3/4 multiplied by Y is representing the number. Okay. Sum means plus. What are we plus into? It says 7. So the whole thing becomes 3/4 Y plus 7. That's the result. Abraham, is it clear now? I can get your feedback.
Yes, please. It's clear now.
Very good. So let's look at the last one, and then I'm sure by the time I'm done with the last one, you would have gotten a lot of things that we can use to solve problems.
Please, can we conclude like this?
Hello?
Yes.
Can I do what?
Can we conclude this way? So, in the example that you gave, 4 more than S. So, can we say that anytime it involves addition, the order is important? When it is minus, order is not important. Can we conclude that way?
Yes. For now, you can conclude that. Because if you don't conclude that way, you'll be running into problems. So let's take it that when it is addition,
Order is important.
yes, order is not important. When it is addition, order is not important. All other operations, order is important. So negative, multiplication, division, order is important. Now let's look at number 7, the last one. 10 times 10 times a number. Ten times a number increased by 150. 10 times a number increased by 150. So let the number represent X. Increase is positive by 150. Now 10 times a number. So 10 multiplied by the number. That's 10 times a number plus increase by 150. We have 10x plus 150. Any question? We minutes. Let's try some small calculations, and then we can move. Now you can be asked to do some evaluations in algebraic expressions. And some of them are very easy, like these ones. It says evaluate each expression for y equals 3. It means that wherever you see y, put 3 there. So if you have 3y plus y, it means your solution will be equal to 3y, means wherever you see 3. And this will give you 9 plus 3. And that is the 12 you are seeing here. So this one, you don't waste too much time. 7y equals, wherever you see y, put 3 there. 7 times 3, and this gives you 21. 10y minus 4y, same thing, 10 into 3 minus 4 into 3. This gives you 30 minus 12, and that gives you 18. Then we have 9y. Wherever you see y, you put 3. So 9 times 3, you have 27. Y plus 5y plus 6y. Wherever you see y, you substitute 3. So you have the following: 3 plus 15 plus 18. Ten y, wherever you see y, you put 3 there. And you finally end with 30. So these are straightforward. These are straightforward substitutions. You don't even simplify them. You just substitute wherever you see y, you put the value there, and then you go ahead. All right. There is also expansion when we were writing the expressions where Abraham drew my attention to this side that we wrote it wrongly the first time. Twice the sum of a number plus 4. Sometimes when you have issues like this, you may have expansions. And so we have to learn how to. It is a product. But to be able to get your answers, you have to release the product into sum so that all the terms will stand. If you have 3 into x plus 2, this is complex. You have to release them. You can't call this one a complete term because you need to expand. In this form, it is in the multiplication form. That's the product. But if you want to change it to the sum, you need to expand. So you have 3 multiplied by x, you have 3x plus 3 multiplied by 2, you have 6. When you do it this way, you can confidently say you have two terms. This is the first term, and then this is the second term. And then you can work. This is called the distributive property. In any algebraic expansion, you have to distribute. So we distributed the 3 over x and then over 2 to remove the brackets. With this, there are more things you can do when it comes to factorizing terms, matching terms, and you want to know how terms can match up to the other in terms of equality. And an example is what I did here for you. That let's see, they were like this. Now we want to find out, are there some common terms? We have common terms for these expressions. Do we have common terms for these expressions? Yes, we do. I want to look at them. Let me look at the first one. Now, I'm saying this 4 into bracket y minus 2 can be represented in this way. It is a difference. In conclusion, they are the same. Whether product or difference, they are the same. Now watch it. 4y, 4 into y minus 2. When we expand this one, we have 4 multiplied by y, we have 4y. 4 multiplied by 2, we have 8. So finally, it becomes 4y minus 8. And that is what we have seen here, 4y minus 8. We can therefore conclude that this product expansion will give us this difference we are seeing here. Another example is the last one. Y as a product multiplying 4 minus 2y. We are saying that it is the same as the difference we are seeing here as 4y minus 2y squared. Let's check whether this is true. If you pick this one, y into 4 minus 2y, and you expand, y multiplied by 4, you have 4y minus y multiplied by 2y, you have 2y squared. And this 4y minus 2y squared is what you are seeing here. Therefore, we can say that the product or multiplication here is the same as the difference or the minus that we are seeing at the side. So sometimes there can be some mapping this way when you want to deal with factorization of algebraic expressions. All right. So we've done enough in terms of the coefficients, the terms, and the expansions. Therefore, let's use this short quiz to see how we can change either multiplication to subtraction or addition. And it can also be the reverse, how we can also change subtraction or addition and make it multiplication. So this can be by we move to the right. Let's work it out here. 3x minus 9. So when I pull 3 out like this, I'll be left with x within, and then this will reduce to 3. If this one becomes my answer, I can therefore say that the thing initially here was minus. We've been able to change it to multiplication because the bracket is multiplying this 3. Initially, there was no bracket, but we have created a bracket, and as a result, this 3 is bringing the multiplication. We can do same thing to this addition, changing it to multiplication. We have 10 plus 4b. This 10 plus 4b, we have all agreed that for addition, order doesn't matter. So we can rewrite this one as 4b plus 10. 4b plus 10. And if we look at this, we can't factorize 4 out, but we can factorize 2 out. When we factorize 2 out, we'll be left with 2b here. And then here, we'll be left with 5 if we pull 2 out. In the same way, we've been able to change addition to multiplication because this 2 is multiplying 2b what number is common to 12 and 18? We can use 6. So we pull 6 out. C squared, that is also common. We pull 1c out. After that, what are we left with? We are left with 6 for the first term, and then we are left with 3c for the second term. This is what we have done. We've been able to change this expression from minus into multiplication.
Hello, sir.
Yes.
So when you are reversing the 6c into brackets 6, when you multiply them, you get 36c, right? Or
You get what?
36.
Oh, sorry. It's an error. It's supposed to be 2.
Yeah.
Thank you. It's 2 minus 3c. That was a quick observation. Thank you.
Thank you.
Right. So then let's look at the fourth one. 20xy plus 6x squared. So 20 and 16, what number is common to them? 4 is common to them. X squared. So x is also common here. Let's look at the rest that will be left within the bracket. So for the 20, we'll be left with 5. And then we have y. The x we have used all plus. Then the 16 will be reduced to 4. The x squared, we've pulled 1x out. So we are left with the other one in. And this becomes the results. So again, we have change addition to multiplication. The moment you get a number outside the bracket, it means you have changed it to multiplication. Let's look at the last one. 5 minus 3, 5 minus 35x. 5 minus 35x. So we have common number between 5 and 35 is 5. So within the area of 5, we'll be left with 1 minus the 35, will be left with 7. So finally, we have 5 into 1 minus 7x. When you expand, you get back this one. And so we have changed it from minus what is within the bracket. And that is the end of our short quiz. Any question? All right. So in conclusion, we want to see how we can factorize quadratics out. We want to see how we can factorize quadratics out. So anytime you are given an expression x plus a multiplied by another x plus b, when you expand, like you know already, x multiplied by x, you have x squared plus x multiplied by b, you have xb plus a multiplied by x, you have xa plus a multiplied by b, you have ab. Now, when we want to make this neat from what we just learned, we have x here, we have x here. So x will come out, and then the inside will be left with b plus a plus ab. And then finally, we have x squared plus. We all agreed this morning that when it comes to addition, order doesn't matter. So b plus a is the same as a plus b. So a plus b x plus ab. Now look at some nice observation here. Watch this side. A plus b, a times b. We are going to use them. A plus b, a times b. What it means is that anytime you expand two algebraic expressions in which the number you have here or the variable you have here, you have the same variable here. And then you have different variables here, like a and b. All you are going to do is you are going to generate 3 terms. First term, second term, third term. The 3 terms you are going to generate, this is what normally happens. This x here and this x here. First of all, you multiply them and then so pick A and then pick B and just add them and put it there. Pick A and pick B and just add them there. For us to know where A and B are coming from, they are coming from X and X. So you record the X here, that this A and B are coming from this X. And then finally, the last step is that just pick the same second numbers in both brackets. And then this time, don't add them, just multiply them to get the side. Now we want to understand it further by working an example. And this is a quadratic equation, whereby in quadratic equation, this is the format. You pick your x squared plus, then you write the sum. Now this A and B, they are called the roots. They are called the roots of the equation. So sum of the roots, just put the roots together. Add it. So sum of the roots of x, and then add it to the product. Add it to the product of the roots. So those of you who remember your secondary school maths, I'm going to do something and use it to explain what we have just done. And then you can follow what we are doing. These are the steps. In factorizing quadratic equations, these are the things you do. First of all, step 1, look. Step 1, let me even write the original equation so you don't get confused from the expansion. From the expansion, let me go back so that you can have a good look at that expansion. This one, let me come back here and write the steps here for you so you can follow. My time is almost up. I don't think I can complete this one. Let me do step 1, and then probably we'll have to continue this side, God willing, next week. But let me finish step 1 with you before we wrap up. So any form of quadratic equation in algebraic form looks this way. And from what we have learned today, there is a sum in the equation and there is a product in the equation. So when you are asked to solve a quadratic equation, what you are seeing on the left-hand side, this is the actual answer they want you to arrive at. This is the actual answer. The actual answer is made up of 2 factors. Factor 1, which is x plus a, and factor 2, which is x plus b. And so how do we change this into this? In other words, if it were written this way, x squared plus a plus b, x plus AB. The answer is x plus A, x plus B. And from what we did before we got here, we said sometimes they can ask you to change either addition or subtraction into multiplication. Or they can also ask you to change multiplication to addition or subtraction. And we've worked examples on this one. These were the examples we were doing not too long ago when we were doing the change. These were the examples. So for instance, this one, it was minus, and we were able to factorize, and then we change it to multiplication. So these ones look very simple. But now we are moving to a more complex zone where we have a lot of terms. These ones were basically two terms, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. But we now want to expand into three terms. So if you look at the three terms, this is the first term, this is the second term, this is the third term. And then we want the answers to become this way: x plus A, x plus B, meaning we want 1, 2, 3, 4 terms. But when you watch this side, it is 3. 1, 2, 3. So the question is, how can we increase this one to 4 terms in order to match these 4 terms here? That is exactly what we were about to do. But looking at my time, we can't proceed. I have 7 minutes more. I want to use it for question time. So let's end this one here. That God willing, next week, we are going to see how we can change these 3 terms into 4 terms in order to be able to match our answer on the right. And like I said, 2 things will be done. We are going to use addition, and then we are going to use product to be able to change this from 3 terms to the 4 terms. Any question before my time is up finally? All right, so if there's no question, I want to end the class here for you to prepare for your next class. On that note, I want to thank you for your participation today, and I wish you the best of the day. God willing, we'll continue next week.
All right, sir. Thank you very much for your time. We really appreciate it. Yes. On behalf of the HRM class too, we say thank you. And then we are willing to, I think I sent you a test last week. So maybe we will talk about that later, please.
Thank you so much for your time.
Let's prepare for the next lecture.